Let's begin. I want to talk about resolution of matrices. So let me tell you what kind of, I'm going to be looking at very special matrices. So A1 is such a matrix. It need not be a square matrix. As you can see, this 3 cross 1. The entries, as you can see here, are polynomials. So let us put m is equal to the number of variables. Here there are 6 in this example. So there is a certain m which will be fixed throughout the talk. It will be the number of variables. And observe also that each one of these is a homogeneous polynomial. That is, each of these monomials is of degree 2. So let's call E1 the homogeneous degree of any entry of A1, which is 2 in this example. Okay, so the matrices that I am going to look at are have entries that are polynomials in m variables, and all the entries are of the same degree E1. Okay, let's make another observation which is going to be important for the next what we're going to do here. The entries here are the 2 by 2 minors of this matrix. So x, y, z, u, v, w, just think of these as variables, and xv minus uy here is this determinant of this 2 by 2. yw minus vz is this 2 by 2 minor of the determinant of this 2 by 2 submatrix. So, okay, what do I mean by resolution of a matrix? So let's do this by example. I'm going to resolve this A1. Okay. What it means is, so you start, so this is an, let's call this R1 cross R0. That is notation for the size of this matrix, 3 cross 1 in this example. So by a resolution, or at least the first step of that resolution, I mean a matrix A2, all matrices will have the same property. They are all, entries are all homogeneous polynomials of the same degree. Need not be the degree for A1 could be different from degree for A2, as we will see, but these properties hold. They are polynomials in the same number of variables, and all entries are homogeneous. Okay, so it must be R2 cross R1. So this R1 is the same as this. The number of columns of this A2 must be the number of rows of this A1, and they must multiply to 0. And furthermore, this is the crucial condition. Suppose I have a 1 cross R1 matrix of polynomials such that xa1 equal to 0, that's matrix multiplication. Then there exists a y such that that x is given as y times A2. Okay? Okay. Now A2 in this example for A1 is this matrix. Okay, so you can check that x, y, z times this is 0, u, v, w times this is 0. Now you can, I've put here cheating. I mean, the fact that A2 times A1 is 0 is just that follows from the fact that these are the 2 by 2 minors of this matrix. So if you expand a 3 by 3 matrix in which the last row is the minors of these, these you put there, then you're going to get 0. Okay, so E2, let's call the degree of any entry of A2. A2 is also such a matrix. All the degrees are 1, and that degree I call E2. Okay. Okay. Now, given a matrix A1, you would resolve it by, you construct an A2 like this, if you can, and then you go on with A2, construct A3 if you can, and proceed. Okay, then A3 to get A4 and so on. Stop if and when x times ak equal to 0 implies x equal to 0. Suppose you have this property, then you can take the ak plus 1 to be 0. Okay, the matrix, and you are done. Okay. Okay. So this sequence, let's call it A1, A2, A3, A4. I should have written it maybe the other way, but since the multiplication is A2 times A1, I'm writing it. A1 is the first given matrix, and then you constructed A2, A3, and so on. Let's call this the resolution of A1. the given matrix A1. Okay, and the degrees of the corresponding entries in this AIs are EI. Okay, in the example above, it's the length is 2 of this resolution. Length is, this K is called the length. Okay, and the degrees are 1 for A2 and 2 for A1. Okay, as you can check, this property, it stops at this point. Okay, good. Okay, so here is a famous theorem of more than 100 years ago, due to Hilbert. Given any matrix A1 of any size with entries all of the same positive degree E1, which could be anything. So you're given a big matrix, all the entries are of the same degree. Okay, that's all that you ask. And then you can resolve it. There exists a resolution. So A1, A2, AK, with it gets resolved in at most m steps, where m is the number of variables. Okay, and for example, in this previous example, K was 2. It got resolved in 2 steps, and we had 6 variables. Okay, so this is called the syzygy theorem. Okay, the resolution is essentially unique. In particular, the degrees Ek, these degrees, and the sizes of these matrices are uniquely determined by the given A1. So once you give me A1, everything else pretty much is fixed. Okay. Okay, and then more than 100 years later, there came this question. One could wonder why this question wasn't asked before, but there it is. Given a sequence of an arbitrary sequence of positive integers, does there exist a matrix A1 with resolution of length m as above, such that the number of variables is exactly m. M is the length of this sequence, notice. Okay, the entries in AJ are homogeneous of the same degree EJ. Okay, these EJs must be the degrees of the entries of each EJ. So let's do an example. M equal to 3, and suppose all the E3, E2, E1 was 1, then here is a solution to this problem. A1, you take x, y, z, 3 variables, m is 3. Okay. A2 you take to be this matrix, and you can check that this resolves this, and A3 to be this matrix, which resolves this. Okay. Okay. Here I've said that the sizes are no bar. I mean, we don't, in this question, the sizes are no bar, but see below. Okay, we have an observation from the 1970s actually shows that if you have for the sizes in such a resolution, the RJ, that's what I mean, are proportional to, are determined by the up to scaling. Okay, this means proportional to. So the formula is precisely here. You put, instead of these EIs, I have just taken these D, you generate these Ds, which are equivalent to the E's, and then you write this expressions. Okay, so note that I have omitted here this is I not equal to J. Okay. So in the above example, if you see, these D's come out to be 3210, and this, if you do this calculation, it is 1 by 6, 1 by 2, 1 by 2, 1 by 6, and the numbers are 1, 3, 3, 1, which is proportional to 1 by 6, 1 by 2, 1 by 2, 1 by 6. Okay? Okay. And here is the final slide. So the answer to this question was given to be S in 2013 by Eisenberg, Floistad. Okay, that's the problem with the X journal rendering. It's Floistad, F is missing, and Wyman, 2013. Strategy, and the strategy is you are not demanding enough. Demand more and the question becomes easier. Okay. I'll say precisely what that means. The key observation is, it's sort of deja vu, the products in Herzog-Kuhl are similar to those in something called the Wild dimension formula. Oh, the problem solved with the Fs. 1920 for GLM modules. GLM, M is this number of variables. Okay? So I guess I'm out of time. So the sizes Rj are dimensions of certain GLM modules. The matrices Aj are interpreted as, instead of just this modules for this polynomial ring, you have this GLM in addition. And then the Peary rule, which is a well-known rule in representation theory, guarantees the existence of the Aj. So notice that we don't know these matrices explicitly, rather we sort of know they exist. Okay? And finally, work with Satish Kumar sitting there, work in progress. We have what we believe is a simplification to the proof of these people. Thank you. And a big hand, please, for all the ISD organizers.
Thanks, Raghavan, for this talk. Can I have one quick question?
Just one observation. If you go back, yeah. See, your definition of Rj is proportional to 1 divided by, that looks like modulus of Vandermonde determinant.
Yes, 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 yes. The Vandermonde, very good. I mean, yes, the Vandermonde determinant is very crucial to the Wild character formula, Wild dimension formula, Wild character formula. Yes, yes.
Interestingly, these Vandermonde determinants are also important in quantum Hall effect. Ajit Balram knows about it.
Ah, okay. Yeah, yeah. Thanks. Yeah.